And a reason why you might want to do it is there's many commercial applications for 3D display or high-resolution 2D display, such as seismic imagery for oil and gas. And mind you, this wasn't a simple raster scanning of an image in 2D. This was not, rapid tiling. This was actually a fairly complex scan mechanism, or at least scan direction. So there's very little prior work done in inverse super resolution. Just about the only thing in the field is wobulation, which is a name that either HP or TI calls the kind of apparent increase of resolution. So in this one technique that had existed, the folks said as follows. They were able to increase the resolution of an image when the resolution of the grid on which the pixels are addressed is increased. In a wobulated projector, for each frame of image data received, multiple subframes of data are generated. Each subframe contains unique image information and is projected onto the screen in a slightly different position by means of an optomechanical image shifter. This increases the addressed resolution, but does not change the pixel size. Pixels from distinct subframes overlap. So HP had this technology that I believe might have also been used in some TI HD resolution televisions, in which a half HD resolution DMD was made to create imagery that sort of looked like HD resolution by vibrating the image back and forth a subpixel. So the native pixel size is still quite large and blocky, but if you integrate, you can introduce new high-frequency information. So we took a different approach. We wanted to have a system in which you truly increase the resolution and the new pixels are tiny as they're supposed to be, so that you don't also impose any low-frequency information into the image that you don't want. The system has several parts. First, there's an Illumination Engine at the top with a DMD in it. An image of the DMD is projected into space, where you see image of DMD. And there we place an optical barrier, which is an array, in our case, of 1,000 by 700 or 800 little tiny holes, matched pitch-wise to the pixel pitch of the DMD, with a really small area. Then there was a vibrating mirror that was a specific angle that underwent a very small sort of sub-degree rotation. Then this was projected onto a screen, and the idea was that a lenticular would then be placed on top of the screen to make a high-res 3D image. And here's what the optical barrier looked like. So when light, this is superimposed on an image of the DMD. So after the light goes through this barrier, you'd see little tiny windowings of the pixels. I used to call it the bed of nails module. So when you turn this on, it was configured in such a way that over several time steps, the scan would happen at a very slight angle, and the imagery from various pixels would line up after about 10 or 20 steps in the scan. So it works by scanning the image of a standard projector at a very slight slope, while minifying each pixel with a microarray of apertures. Here at time equals 0, you can see the footprint of a standard projector pixel, which is blacked out, and just this one little high-density reduced size pixel that shines through on what is really a trapezoidal pixel grid rather than a rectangular one. It's sort of like a sheared rectangular grid. At the next time step, the square moves, and at the next time step, the square moves again. And when you have this happening for an array of many, many pixels, they will actually line up after about 25 or so time steps. So before I show you the result, here's what the prototype looked like. There was a driver from Violux, which is a company in Germany, that helped us control the DMD. Its image was projected into the space, into an accessible image plane, using a relay that we had on hand. It happened to be a catadioptric relay assembly, but you don't necessarily have to use something that complicated. That would strike a mirror, which would then rotate and go through a high-quality projection lens. Here's the image that it created. It's 5,120 pixels by 3,840 pixels, which is a large multiplier over the original. The color was good. It suffered from brightness losses because each aperture was maybe 1/25th the area of each pixel. But I thought it looked pretty good. Once you have the high-resolution 2D image, you can create a 3D image by putting a screen, such as a lenticular screen, on top of it. So now let's look at a very different type of 3D image creation, whereby a lenticular performs, view interleaving, or whatever the correct terminology is. You can also scan a sequence of images over an angular extent, so that wherever your eyes are, you would see either instantaneously or integrated over a time period an entire field per eye. So let's learn about this from the standpoint of rather than seeing an entire field at once, looking at a display whose optical properties vary in time. There's you can call this whatever you'd like. I call it piecewise lightfield reconstruction. Here's an example of how you'd make one dot, one voxel of an image float in space. This is a top-down view. On the left you see the dot you'd like to reconstruct, which is numbered 760. There's the image plane, or the display surface, which is 701, and the observer on the right. As you can see, if there was a real dot floating behind the screen, it would be sort of approximatable by a series of rays which leave that screen, so you could see that they're going in a variety of different directions. Likewise, if you wanted to reconstruct the dot 750, which is in a different position, it would generate rays leaving that screen at 3 different directions. So, sounds easy to say it, but all you need to do is generate a display that can, over time, create rays of light that leave the screen in those angles as shown, and your eyes and your brain will actually interpret that as a dot floating inside the display. You can also make images look like they're floating at different depths, as you can see by the rays drawn here. Finally, of course, you can make imagery float in front of the display, sort of in the air, and you could bring your hand up to touch these images. To do that, the rays simply go in a yet different set of directions. So when we realized this, and I think a collection of people have realized this, we decided to test our understanding by building a brute force simulator of this. We built a 198 view multi-view display. It had several parts. On the left it had a DMD, which would show a scene from a variety of different viewpoints. It had a scanning galvo mirror in the middle, which would rock back and forth. And then there were some re-imaging optics that would project that imagery out so it's straddling a vertical diffuser. The role of the vertical diffuser is to spread out the light up and down so that when you move your head up and down, you could still see the image. If the vertical diffuser wasn't there, you would only see about 1 or 2 rows of the image, because that's the only light that will be entering your eye. And here's the ray trace of the system. The DMD is at the lower left. It's illuminated. Its light is then imaged onto a scanning mirror, and then there's a re-imaging and magnification step that throws that to a vertical diffuser. And I can't guarantee that this animation will work when uploaded to YouTube, but here are 3 time steps of the image. So you can see over 3 time steps, or over 198 time steps, you can program light to leave in whatever direction you want to leave, and that gives you a programmable light field. This system worked. Even though it was really modest and only made images about 1 inch cubed, it certainly made pictures that could float in the air. This was an image from an OpenGL-based software library, which is standard, using just 1 PC rather than a bank of hundreds of PCs, that was able to project the words perspecta and actuality floating around a torus. It's green because we used a green diode laser to control this system. And at the top is a stereo pair that you could try to fuse.